Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson number 4 on exponential functions. Before we begin, let me remind you that you can find a copy of the worksheet that goes with this video, along with a homework assignment, by clicking on the video's description. As well, don't forget about the QR codes at the top of each one of our worksheets. Use your smartphone or your tablet to scan that code, and it'll bring you to the video associated with the lesson. All right, let's begin. So there are many different types of functions. The ones that we've studied the most often have been linear functions. But there are also exponential functions, which are really based on repeated multiplication. And those are the ones that we're going to dig into today. Let's start in exercise 1 by looking at the function f of x equals 8 times 2 to the x. Letter A asks us to just evaluate this function at a variety of inputs. So what I'd like you to do is pause the video right now, spend up to 5 minutes, shouldn't take you that long, but spend up to 5 minutes to work out, subproblem 1, 2, and 3. Pause the video now. All right, let's go through them. So, a little bit of review on function notation. F of 2 is 8 times 2 to the second. Order of operations dictates that we do that exponent first. 2 to the second will be 4. And then 8 times 4 is 32. We also need to come up with the point that must lie on the graph of f of x based on each. That's simple enough. When the input is 2, the output is 32. All right, let's do f of 0. That's going to be 8 times 2 to the 0. Again, we have to do that exponent first, but here it gets a little bit trickier because you have to remember from a couple lessons ago that anything raised to the 0 power is 1. It's very important to make sure that you do 2 to the 0 first and then multiply by 8, because that gives us 8. That gives us the point 0, 8. I also want to emphasize, though, because this will be important later on, that also happens to be the y-intercept, right? The y-intercept always occurs when x is equal to 0. All right, let's do one where the input is negative. F of negative 1 will be 8 times 2 to the negative 1. Now remember, negative exponents indicate that we're going to divide 1 by 2 to the first, but then 8 times 1/2 is 4. Telling us that the point negative 1, 4 also lies on this graph. All right, let's jump into something that we haven't done for a little while. Average rate of change. Average rate of change. Let me do something down here. Average rate of change, right, as we go from x equals a to x equals b, is just the slope formula. It's the y value at b minus the y value at a divided by b minus a. This is just the change in the y values divided by the change in the x values. So if we want to calculate the average rate of change from negative 1 to 0, that's pretty easy. Because we know at negative 1, our y value is 4. We know that at 0, our y value is 8. So if I'm finding the change in y divided by the change in x, I can just do 8 minus 4. Now watch out. Divided by 0 minus negative 1. So that's going to be 4 divided by positive 1 for an average rate of change of 4. On the other hand, if we want to calculate the average rate of change from 0 to 2, again, let me write down my 2 points, 0, 8, and 2, 32. Then the change in y divided by the change in x will be 32 minus 8 divided by 2 minus 0. 32 minus 8 will be 24 divided by 2 gives me an average rate of change of 12. Now, letter D is very important. It says, what does comparing the answers from B and C tell you about this function? Explain. I want you to think about this a little bit. All right. Well, it tells me one thing very specifically. It might tell us more as we get to understand exponential functions more, but it tells me one thing very specifically. This is not a linear function because its average rate of change, I wish that wasn't so long, because if its average rate of change is not constant, right? We've only really studied one type of function, which is linear. And what makes a linear function linear is that its average rate of change is always the same. And in fact, it's its slope, the m value, if you will. But here we see that our exponential function has a much larger average rate of change on the interval 0 to 2, right, an average rate of change of 12, as opposed to the interval from -1 to 0, where it's only 4. Now remember what those average rate of change are telling you, like the average rate of change of 4 is saying that for every 1 unit of increase in x, y is increasing by 4 units. On the other hand, an average rate of change of 12 tells me that for every 1 unit of increase in x, y is increasing by 12 units. So much faster, much faster. All right. So there's a lot of important information in this problem. Pause the video now, take some time to think about it and write down anything you might have missed, and then let's move on. Okay, here we go. Now, the last part of this problem is to examine a graph of an exponential function for the first time. And what we're going to do is initially, we're going to do this with our calculator. So letter E says, using your calculator, draw a sketch of this function on the axes below using the window indicated. All right, great. So what I'm going to do is I'm going to open up the TI-84 now. Watch this. And there it is. It's like magic. So we've got our TI-84 plus opened up. I'm going to go into y1 now, or I'm going to go into y equals. I'm going to clear out any formulas I might have in y1, y2, etc. All right. And now let's enter that formula into y1. Okay, so go up to y1. Let's be very careful. We're going to put 8. I'm going to actually enter it more or less the way it looks. I've got that 8 in. Now I'll put parentheses, 2, parentheses. And then I use this caret button here. This is the button that I use to indicate that I want to raise something to an exponent. So I hit that button. Why it's called a caret, I'm not exactly sure. But I hit that button, and then I have that raised to the x. Step back, really look at the formula, make sure it looks good. All right. And now I'm going to go in and adjust my window. So let's hit the window button. Remember, it's right up here. The beautiful thing is that the problem gives us the window, right? We want to set our x min to be -4. Our x max is going to be +4. Okay, go down a little bit. Our y min is going to be -10. And our y max is going to be 130. All right. Once you have the window all set, do a double check, make sure it's right. Okay, let's see what this thing looks like. Let's hit graph. Graph. Takes a little bit for it to come up, but there's your classic exponential graph. You're going to get very, very used to seeing this. Not sure why it just cleared the page, but looks something like this. I remember once, hopefully it looks a little bit better than that. I remember once teaching calculus and a student describing this as the hockey stick looking graph. All right, I'm going to in fact mark my y-intercept on it. Okay, that was 8. Right, that was this number right here. So I realize this is not exactly drawn to scale, but it's not too bad. We're going to see that looking graph again and again and again. This graph that looks a little bit linear, but definitely has some curve to it. Okay, probably a lot more curve than what I just drew. Anyhow, I'm going to get rid of my TI-84 plus now with a snap. Okay, my calculator is gone. I'm going to clear out the screen, and then we're going to summarize. All right, let's take a look. Exponential functions. Your basic exponential function has 2 parameters, just like your basic linear function does. Now, they tend to be called a and b. I apologize if this is confusing with, your y equals mx plus b. This b and this b have nothing to do with one another, all right? So cross that out. But let's talk about these two exponential parameters. All right. A, the number sitting here, is actually the y-intercept. And the reason it's the y-intercept is that if we put 0 in for x, which is where we always get our y-intercept, then this will always equal 1. So we'll always get a times 1, which will give us a. So that number is the number we begin with. It's our y-intercept. When we were talking about rumors spreading, it was the initial number of people who knew the rumor. When we talked about Helmet walking that weird half-distance thing, it was 160 feet, if you remember that from our last lesson, if you were even with us for that last lesson. Anyhow, then you have b. b is the multiplying factor, the base. It's what you're multiplying by again and again for a unit increase in x. So for instance, again, if we take us back to the rumor spreading, b was 2 because we were doubling for every unit increase in x. Sometimes it's known as the growth factor, sometimes it's known as the decay factor. There's lots of little names given for it. But honestly, it's what you multiply by each time you increase x by 1. That's all. So I'm going to clear this text out, copy down what you need to, little notes here and there. All right, let's do it. Okay, that's gone. So let's get into some problems now. Okay, exercise number 2 says consider the function g of x equals 54 times 1/3 to the x. Okay, letter A says evaluate g of 0. What point does this indicate on the graph of g? Why don't you go ahead and do that? All right, well, I hope that was quick. We just sort of talked about this, right? G of 0 is 54 times 1/3 to the 0. 1/3 to the 0 is going to be equal to 1. And 54 times 1 is 54. So that indicates the point 0, comma 54, but more importantly, it indicates the y-intercept. Emphasizing again that that number is what we start with. It's our y-intercept. Now, the second part says, without the use of your calculator, determine the values of g of 1 and g of 2. Try to do that, okay? Try to figure out what g of 1 is and what g of 2 is. All right, let's work through them. Well, g of 1 is going to be 54 times 1/3 to the first, but 1/3 to the first is just 1/3. And of course, multiplying 54 by 1/3 is the same as dividing 54 by 3. So we get 18. G of 2, on the other hand, will be 54 times 1/3 to the second. Remember, we have to do that exponent first, which will be 54 to the 1/9, right? So 1/3 times 1/3 is 1/9, and if we do that, we'll get 6. Now again, notice, right, we started at 54, divided by 3 to get 18, right, or multiplied, better yet, by 1/3 to get 18, multiplied by 1/3 to get 6, okay? So let's take a look at letter C. Again, what we're going to do is we're going to open up the TI-84 Plus, and we're going to graph this function using our TI-84 Plus. I know there's not a lot of room on the screen, so I apologize. I'll get rid of the calculator pretty quickly. I know I got to cover up letter D right now. But just like before, what we're going to do is we're going to go into y equals. We're going to clear out our equation from last time, so let's do that. All right. And now we're going to enter in our new function. Very, very important that we enter it in correctly. So let's do it. We put in 54, parentheses, 1 divided by 3, parentheses. Then we use that caret button again to raise that 1/3 to the x. All right. Step back, make sure you look at it. It is extremely important that you have those parentheses around the 1/3. Okay? So we've now got 54 times 1/3 to the x, and we now have to set our window. Now in this problem, instead of giving you the window on the axes themselves, I'm telling you what the window is, so let's do that. Let's go into the calculator, and into the window, right up here. Let's put in for x min, -2, For x max, we'll put in positive 4. Okay, make sure we've got those two. Now we go down a bit. For y min, we're going to put in negative 10. And for y max, we're going to put in 100. All right, so we've got our window set. We've got our function in properly. I think it's time to graph. So let's do it. Graph is up here. Let's hit it. Graph. Takes a little bit of time, but what we end up seeing is a graph that is very, very similar to our last one, but now that hockey stick, if you will, kind of looks more like this. Our y-intercept is 54. Right? So we've got my 100 up here. We've got my negative 10 down here, my negative 2 here, and my 4 here. Now, letter D is very, very important. Why is this exponential function always decreasing while the one in exercise 1 is always increasing? Well, let's make sure we get rid of the calculator first. It's gone. And now let's answer this. Why was it that this function was decreasing, always, right? Always going downhill, this function, whereas the one in our first exercise was increasing? Well, in this case, it was because our base was less than 1 in this problem and greater than 1 in the previous problem. Now watch out. Some people will jump to an incorrect conclusion. Not so much an incorrect conclusion, but an incorrect statement. They'll say something like, well, in this case it was decreasing because the base was fractional, and in the last case it wasn't. It doesn't have anything to do with fractions. It has to do with a very simple fact about multiplication. If you multiply by a number greater than 1, the result will increase. If you multiply a positive number by a number greater than 1, the result will increase over what you started with. On the other hand, if you multiply by a number between 0 and 1, I'd like to just say less than 1, but then that would include negatives. But if we multiply by a number between 0 and 1, then the result we get decreases. We can summarize that in the little box that we have sitting here. Y equals a times b to the x will increase if b, the base, is greater than 1. And it will decrease if the base is between 0 and 1. All right. Now, the skeptical student would say, yeah, well, what if the base is equal to 1? Well, if the base is equal to 1, then nothing is happening, right? If you just keep multiplying by 1, nothing changes, all right? So we increase if the base is larger than 1. We decrease if the base is between 0 and 1. I can't even tell you how important this is, all right? Probably should have gotten its own page because of how important it is, but make sure to know this. This is sort of the equivalent of saying that a linear function will increase if the slope is positive and decrease if the slope is negative. Here it's about whether the base is greater than 1 or between 0 and 1. We'll never have a base that's negative, all right? And it'll actually be rare, especially in modeling problems, for the y-intercept or the starting amount to be negative. So we won't be too worried about that. All right, lots of important stuff in this problem. Pause the video now to think about it and write down anything you might have missed. Okay, let's keep going. So we just saw some really important stuff, all about what's the y-intercept and does the function increase or decrease. So just a real quick check on that, whether or not you've got that. Exercise 3 says for each of the following exponential functions, give its y-intercept and tell whether it's increasing or decreasing. All right, well, what I'd like you to do is pause the video right now and see if you can do these. They're actually very, very quick. If you're still confused, we'll go through letter A and then we'll pause again. Pause the video now if you think you understand what's going on. All right, let's go through it. So this is how easy it is. It's kind of like identifying the slope and the y-intercept of a line. Here's your y-intercept. My y-intercept is 8, and it is decreasing because 2/3 is less than 1. I'm not going to say it's between 0 and 1, it's less than 1, right? 2/3 will force that 8 to get smaller. All right, do you get it? So pause the video now and see if you can do B and C if you haven't done them already. All right, let's do them. So in this case, my y-intercept is 125, and we're increasing in this case because 1.5 is greater than 1. Pretty much that simple. Letter C, the y-intercept is equal to 56, and again, we are increasing because 3/2, which is the same as 1.5, I only realized that now, is greater than 1. I mean, I know 3/2 and 1.5 are the same, I just didn't realize I used the same base there, because 3/2 is greater than 1. All right, so it's very, very important. It's not about fractions, it's not about decimals. The increasing and decreasing nature of exponential functions is all about whether that base is greater than 1 or between 0 and 1. If it's greater than 1, the exponential function increases. If it's between 0 and 1, the exponential function decreases. All right, so I'm going to clear this out. Pause the video if you need to. Okay, here we go. All right, last problem. We're going to be doing this a lot in the future, but finding equations of exponential functions. Think of all the equations of linear functions we've found at this point. Now we're going to do exponential functions. All right, so we want to figure out the equation in a times b to the x form. Again, what I'd like you to do is I'd like you to actually pause the video now and see if you can come up with the equation. I know that we haven't done this yet, but you do have all the knowledge you need for it. The beautiful thing is, once you have the equation, you could test it on a variety of different points. But pause the video now, take a few minutes to see if you can do it. All right, let's go through it. Well, what we really have to do is we really have to understand the two parameters. A is the y-intercept, right? It's what we have when x is 0. B, on the other hand, is the multiplier, right? It's what we're multiplying for a unit increase in x. So A is quite simple. It's 10, right? It's the value when x is 0. All right? On the other hand, B can be found by thinking about what we do to go from each one of these y values to the next one. And what we're doing each time is we're multiplying by 3. So B is 3. So this exponential function is y equals 10 times 3 to the x. And you could test it. You know, one of the things that you could do is you could say, well, if I took x equals 3 and I plugged this in, I'd get 10 times 3 to the third. 3 to the third is 3 times 3 times 3, which is 27, and I'd get 270. Right? So it's a good check. All right. We're going to get a lot more practice on that in the coming lessons. So pause the video now, write down what you need to. Okay, here we go. All right, let's finish up the lesson. All right, so in the lesson today, what we learned about were general exponential functions. Functions that can be modeled with equations like y equals a times b to the x, where a is that y-intercept, and b is what you're multiplying by each time to get a unit increase in x. All right, we're going to work with these a lot in coming lessons, so you'll get a lot more practice with them because there are many phenomena out there that can't be modeled with linear functions. For now, though, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. Until next time, remember, I'm Kirk Weiler. Keep thinking,